Okay, so good afternoon and welcome to the third lecture series of the ICTS Gravitational Wave Summer School. It's a great pleasure to welcome Professor Frédéric Daigne, our speaker this afternoon from Institut d'Astrophysics de Paris, IAP Paris. Frédéric has been a faculty member at IAP since 2002. He's a leading expert in GRB Physics who has worked on almost all aspects of the wide range of gamma-ray burst phenomenology. He has made pioneering contributions on the dynamics of GRB jets in explaining burst spectra through the synchrotron and compton processes, afterglow phenomenology in using GRBs as cosmological probes, to name a few. He's also the mission scientist from the French side of the French-Chinese Swarm GRB mission to be launched in another 2 years, which is expected to be the next backbreaking satellite dedicated to GRBs. We are lucky to have you, Frédéric, with us. It's unfortunate that we couldn't have the real world meeting. In fact, I was looking forward to have you at ICTS and continue our discussions. Thank you so much for agreeing to give these online lectures at these particularly stressful times. Now to the participants, please switch off your microphones, keep your video off. Frédéric is willing to take questions during the lecture, so type down your questions publicly in the chat box. Or you could also ask the question by raising hand using the hand raise option in Zoom. If you're asking questions, speak slowly and clearly. Those of you watching through YouTube live stream, you can try typing your questions in the window next to the video. We'll try to see if they can be accommodated. And that's for now. To you, Frédéric.
Okay, thank you very much, Resmi, for this introduction, and thank you for the organizer of this summer school. I'm very pleased to give this lecture, even if I'm still in Paris and not in Bangalore. But I hope it will work. So when I'm giving such an introduction on gamma ray burst physics, I like to start with these two beautiful painting from Kandinsky in the 20s. I like that because, of course, I find these two paintings really beautiful, but I also consider that they give a very interesting anticipation of the kind of physics I would like to discuss with you. You see, we will discuss complex phenomena, high energy phenomena like gamma ray burst, and these two paintings say already a lot of things. As you can see on the left, clearly we will see that the main ingredient at the beginning is a cataclysmic event leading to the formation of a compact source, a black hole or maybe a neutron star. And it is clear that Kandinsky had already anticipated the two main channels. I have tried to indicate with an arrow something which really looks like a stellar core collapse, maybe with some hint for asymmetry. And on the top left, there is a clear binary system which is in the process of merging. So we have the two main channels for gamma ray burst. And then with this second painting, Kandinsky tells us that somehow with a complex physics, which is far from being completely understood, the final result, the central engine which is formed after this event, is able to produce a relativistic outflow, relativistic ejecta. And the relativistic ejecta is well apparent on this second painting on the right. And a lot of information in this painting. Clearly, there is some internal dissipation in the blue jet. And we will see that it plays a role for the prompt emission of gamma ray burst. And in fact, Kandinsky has indicated with some red triangles that there is some emission from the jet itself. And clearly, there is also a very strong and important ingredient, which is the interaction of the outflow with the Kirchhoff-Burst environment. And on the painting, we see very clearly a nice forward shock propagating in the ambient medium. With many, you can imagine that some triangles just indicate the orientation of the observer who is trying to detect this event. And Kandinsky says something which has become really of interest since the opening of the multimessenger era with electromagnetic and gravitational waves. The fact that sometimes the observer can be off axis, and I have shown an example with my pink arrow. And finally, I think that the most important thing in these two paintings is the fact that there are many details in the painting that I cannot identify, and it's probably a clear indication that there is still a lot of things to understand about gamma burst. So I will try during these three lectures to cover several topics, which are summarized here. So today I will try to give a very general introduction on gamma ray burst. I will focus on the most important observational facts, and then to build the main constraints that you have to take into account if you want to build a physical model for gamma ray burst. And I have already listed most of the ingredients in this short discussion about Kandinsky. And then in the two next lecture, I will go more into details for some topics. I will probably spend more time on emission during the prompt and afterglow phase than about the physics of the progenitor and central engine relativistic ejection. And I will also, I plan also for the third lecture to spend some time about the connection between short gamma ray burst and binary neutron star merger, what we learned with the event 170817, and I will try also to discuss also the consequences of what we have learned with this event about our understanding on the whole gamma ray burst population. So it will be for the third lecture. So to start, maybe a few words about history, about the discovery of gamma ray burst. It's well known, but it's always nice to hear. So you know, it just after the crisis in Cuba, there are the first attempts to have treaties limiting nuclear weapon test. And the first one is the Treaty of Moscow in August 1963. You can see that, of course, the treaty is an agreement between several countries, mainly United States and Union of Soviet Socialist Republics, also United Kingdom. For instance, France at that time, my own country, was carrying still a nuclear weapon test in Sahara, and so joined this series of treaties much later. So I won't comment policy about nuclear weapons, but what is interesting for us is the fact that the first article says that each of the parties undertakes to prohibit, to prevent, and not to carry out any nuclear weapon test explosion. And then they list all placed under jurisdiction or control. It's very interesting to understand the spirit of mind at that time, because you see that it's very extensive, the atmosphere beyond its limits, including outer space. This is what is called to be powerful at that time. And then, of course, what is interesting for us is that immediately both the USSR and USA developed their own program to check if indeed the treaty was respected. And there are several ways to detect nuclear tests. but one which is of interest for us is to detect the gamma ray emission associated with the explosion. And so the idea was to send satellites. It was the very first generation of the gamma ray satellite. So it's mainly detectors which are capable to say, okay, we have detected gamma ray photons. Probably if with a well-adapted electronics, they can count how many photons, they can evaluate the energy of these photons. But for instance, they cannot at all give any information about the arrival direction of these photons. That's why they sent several pairs of satellites, first to have a better coverage of the surface of the Earth, and second, to be able to have a crude idea of the localization by triangulation, by comparing the arrival time of photons on different satellites. So probably they detected a nuclear weapon test, but I don't know that. But these Vela satellites detected the first gamma ray burst. So you have the light curve of the very first gamma ray burst in 1967. A lot of information is already there. You see that it's a short event, less than 10 seconds. You see that it's extremely bright. You have to remember that it's the very first generation of gamma ray detectors. And here already the signal to noise ratio of this event is extremely high. Also, even if the time binning is not very good, it appears clearly that it is a variable event. We see at least 2 episodes in the light curve. So, as probably you know, it's only in 1973 that the discovery paper was published, because I mean, for the main purpose of this Vela program was a military purpose, so they were not so much interested in astrophysics. And then, of course, in the 70s, in the 80s, many satellites observed gamma ray burst, and this is where we started to better know these events. And I would say that the main mission at the end of the 20th century was the BATSI experiment on board the Compton Gamma Ray Observatory. We really learned a lot about gamma ray bursts with BATSI. And it was complemented very nicely by BEPOSAX for the Afterglow. I will come back to that. And currently, there are several missions observing gamma ray burst, including an Indian one with AstroSat. But I would say that the 2 main missions are still SWIFT and Fermi, which are providing a very good coverage of both the prompt and afterglow emission. So I will start by trying to list the main observational facts, and I will really do the minimal list to have all the information I need to then deduce the basic ingredients of the physical model. So I will start with the gamma ray burst itself, the so-called prompt emission. So again, a famous animation where you see the gamma ray sky. It is in galactic coordinates, so you see clearly the diffuse emission of the galaxy plus a few point sources. And then, if I come back and I start again, you see clearly a source outside the galactic plane, which becomes suddenly extremely bright, again for less than 10 seconds. Probably you notice that at the maximum, it just saturates the detector, so the image becomes entirely white. Again, you see that the signal to noise ratio is very high, and you see that we start to have a better information on the light curves. There are several episodes, several pulses, so clearly we have a very variable phenomenon. We have now catalogs of several thousands of bursts. And for instance, the first big catalog was obtained with BATSI. And a very important result is the following diagram showing the number of bursts as a function of their duration in the soft gamma ray range, typically here between 50 and 300 keV. You see clearly that it is a bimodal, at least bimodal distribution, and it's not a selection effect. There is no reason why BATC would be less efficient for burst with a duration of about 1 second. So there are clearly two groups, and it's a very important fact for gamma ray burst physics. The properties of the gamma ray emission are very similar for the two groups, except of course for the duration. The duration is typically 100 milliseconds for the first group, the so-called short gamma ray burst, and typically a few tenths of second for the second group of long gamma ray burst. And the main difference for the prompt emission is about the spectrum. On average, short gamma ray bursts are harder, but it's a tendency. It's a complex tendency of hardness duration correlation. And then we'll see that the properties
of... There is one question.
Sorry, yes?
There is one question from Ankur Ghosh, that whether when Bala detected the photons, how did they differentiate that these photons are coming from astronomical source and not from a terrestrial source?
So it's a good question. We should come back to the whole paper in '73 where it is discussed, because I remember that in the abstract they can already eliminate a few sources, not only the Earth but also the Sun and the Moon. Probably they use the fact that if the burst is detected by several satellites, using the difference of arrival time and knowing the speed of light, they can have an estimate of the direction. It's probably not very accurate because the distance between satellites is not so large. They are in orbit around the Earth, but it's already enough to have a rough estimate of the direction. And so probably it was done like that. But to have a more accurate answer, we should come back to this historical paper. Is it okay? Is it clear? Yeah. So then I will go on with the properties of the prompt emission. So I discussed the duration, and yes, I was saying that there are more differences for the afterglow that I will discuss later between short gamma ray burst and long gamma ray burst. And the general idea is that probably we have two classes of initial events leading to the same kind of physics regarding the physics of the central engine, the relativistic ejection. And then as the two classes are different, the two classes of initial events are different, the environment is different. And as we will see that the afterglow is due to the interaction of the relativistic jet with the environment, it leads to more differences for the emission of the afterglow. It's a general idea, it's well validated by some observation, but still there are many open questions. For instance, it's not very clear to know how similar is the physics. Is it exactly the same physics, except that, for instance, the central black hole is less massive and the surrounding accretion disk is less massive in short gamma ray burst? Or are there other differences regarding the properties of the jet, for instance? It's a very complex question. And we could learn about that for short gamma ray bursts with multimessenger observation. So here I show a few examples of light curves, again from the BATC catalog. The first one is a short gamma ray burst. You can see that the duration of the event is less than 100 milliseconds if you look carefully at the x-axis. And the three other cases are long gamma ray bursts. These light curves are very variable. they can often be decomposed as a superimposition of several pulses, which usually have a fast rise and a slower decay. And I will discuss in the second lecture the fact that we also observe an interesting spectral evolution during the emission of such a pulse. And then the complex light curve is a superimposition of many pulses like that. And depending on the signal to noise ratio, it's more or less easy to distinguish all the pulses. And a very important question, which is not easy to solve, is to know what is the minimum time scale for the variability. I see that there is a question about the starting and stopping time of the burst. It's an excellent question. Usually what people do when they analyze a gamma ray light curve like that is that they plot the cumulative number of counts after modeling the background, which is not always easy and needs to know very well your satellite and your orbit. And once you compute this cumulative number of counts, usually you observe initially a plateau, then a rise, and finally a plateau. And so you can determine the starting and stopping time from the location of the plateaus. And usually what is done is that from the difference of level between the two plateaus, you can define something which is called the photon fluence, the total number of photons received for the event. And the convention which is usually used for gamma ray bursts is to define the times where you reach 5 and 95% of this total number, and you define the duration as the difference between these two times. This is the so-called T90 indicator for the duration, 90 for 90% of the fluence. But of course, it's just a convention. It's very difficult to determine that precisely. It depends on your instrument, because depending on the energy range, you do not see the same light curves. I will show examples. And there are a lot of debates about possible precursors, which are found, for instance, with an offline analysis of the data, things like that. So very complicated questions. So important is to compare a gamma ray burst with the same indicator for the duration. So for instance, not only the same T90, but in the same energy channel. Otherwise, it's complicated to compare.
Frédéric, there's one more question.
Yes, I see it. I will discuss that a little later because I will show some observation explaining how we know they are extragalactic. So I will answer that later, and if it does not fully answer, you will ask again the question. Okay. So I can also show an example of a gamma ray burst spectrum. So on the top, you have the photon number per unit energy and per unit time. And on the bottom, you have the same multiplied by E square. So for people who are more familiar with optical observation, this is the equivalent for gamma ray astronomy of the standard nu F nu diagram, the bottom diagram. And I see that there is a question about the variability, the variety of light curve. It's true that each light curve is variable, but there is also a great diversity of light curves. It's a very fundamental question for gamma ray burst. I will try to discuss that when I will discuss models for the prompt emission. It's probably related to the behavior of the central engine, I will say. And so for the spectrum, you see that it's clearly not a black body. So bad news, it's not easy to deduce physical conditions from the spectrum. But good news, because it means it's very interesting physics. We are in front of a cosmic accelerator where some particles are outside the thermal equilibrium. And it's always very interesting. It's, of course, common in high energy astrophysics. And you see that the spectrum seems to be well fitted by several power laws, which are smoothly connected. So Usually, the low energy photon index is called minus alpha, and the high energy photon index minus beta, and they connect at an energy which corresponds to the maximum of the new FNU spectrum, which gives an idea of the typical energy of photons carrying most of the energy, and this is usually called the peak energy, E-peak. So here it was a very brief summary of observation of the prompt emission in the soft gamma ray range. One word about other spectral ranges. It's very difficult to catch the optical prompt emission because, of course, usually optical telescopes have a narrow field of view. And so you need some time after a gamma ray burst alert to point a telescope, an optical telescope, towards the source. There are some attempts with a large field of view, with camera with large field of views, and so there are some cases, but it remains rare. It's something we hope to improve with VOM because we will have a set of dedicated cameras following the field of view of the camera instrument. So here I show the best example. It's a case where by chance an instrument, an optical telescope, was looking at the right direction in the sky at the right moment. So it's a pure chance. And so it's a bright gamma ray burst. You see the light curve in black here. It's a long gamma ray burst, which is highly variable for at least 60 seconds. And in red, you have the optical light curve with a very fine time resolution. Usually, we don't have such a nice time resolution for the few cases where the prompt optical emission is known. And you see you have an axis in magnitude, and you see that at the peak, the magnitude is something like 5.3. So it's a very interesting case because this burst, we know the redshift. It's a redshift which is almost 1, so it's clearly a gamma ray burst which occurred in a very distant galaxy. But you could have observed this event with your naked eye. You just would need to look at the right direction in a few seconds. So, of course, to my knowledge, no one detected it, but it was possible in principle. That's why it's called the naked eye burst. It's a very extreme case, but it illustrates how bright the gamma ray bursts are. I will say later, it's still true that gamma ray bursts are the brightest electromagnetic phenomena known in the universe. And this is a very good example. But in the few other cases, there is a great diversity of behavior. Sometimes the optical emission is above the extrapolation of the soft gamma ray spectrum. This is the case for the naked eye burst, and sometimes it's below. So again, it's quite complicated to relate both. I see a question about E dot. Yes. Okay. I think it refers to this slide about the spectral model which is used to feed the data. You see that there is a dotted line. So I didn't give details about that. Here it is fitted with a phenomenological function which is widely used in the gamma ray burst community, which is called the bound function from David Bound, who introduced this phenomenological function. It's a function with 4 parameters, an amplitude, and 2 slopes, alpha and beta, and a break energy. And E-peak, which is plotted on my diagram, can be directly related to alpha, beta, and this break energy. And so I can provide for next lecture if you want the detailed equation, but there is a simple mathematical relation between these parameters. So I think this is what I don't know if Dibita Saraogi can explain better, but I think that E dot refers to that, or do you refer to something else? I'm not sure. Does it answer your question? Or? Okay, I will go on, and if you want,
I guess that's okay. Yeah.
Yeah, and if you want more details, you will ask. Okay, so it was for the optical emission. And on the other side, we made recently a lot of progress about the high energy prompt emission, thanks to Fermi, because Fermi has not only a gamma ray burst monitor, but also the main instrument, the LAT. And the LAT has observed a few gamma ray bursts above 100 MeV during the prompt emission. So it says a lot. It's a very important constraint to better understand the radiative processes at work. I will come back to that in the second lecture. I show here a good example, which is the first gamma ray burst detected both by GBM and LAT in 2008. So you see, this is the light curve of the same gamma ray burst, but in different energy channels. So the two first panels are from the GBM instrument. So it starts at 8 keV and it goes up to a few MeV, okay? And then the three panels on the bottom are for the LAT instrument. For instance, the two last panels corresponds to photons above 100 MeV and above 1 GeV. You see that above 1 GeV, the statistics is not so good. I don't know if we can still speak of a light curve, but clearly there is some signal. I mean, photons are detected. It's very interesting to look at these plots because you see that the light curves evolve with the energy channel. And this is clearly a signature of an underlying spectral evolution. The spectrum is not constant during the prompt emission. And this is something that I will discuss in more details in the second lecture because I consider that this is a very important constraint to try to distinguish between the various models of emission. The light curves here are light curves.
Please mute everyone.
I think that there is a question about the fact that the count number is sometimes negative. It's just because these light curves are background subtracted. And of course, statistically, you can have sometimes after the subtraction, some bins with a negative number. This is within error. Okay, thank you. So, so I will come back in the second lecture on this Fermi observation because, as I said, it gives very interesting constraints on the prompt emission models. So here it was a summary of the most important facts regarding the prompt emission. And now I have to introduce something I have already mentioned, which is the afterglow and the possibility to know the distance of these events. Because until 1997, nothing was known about the distance of gamma ray burst. And it was a major problem for the physical understanding. And for instance, until the beginning of the 90s, there were at least two classes of models which were completely different. Some were galactic models and some were extragalactic models. And this is with the afterglow that the final answer was known. So as often in gamma ray astronomy, the main problem can be summarized with a real estate agent's mantra: location, location, location. That's the most important. So here I have taken a picture from a grid debate which was organized in 1994 between Bohdan Pashinsky on the left, who was among the first, or maybe the first, to propose extragalactic models for gamma ray burst, and on the right, Don Lamb, who was a deputy of the mainstream model at that time, which was galactic, and the moderator is Sir Martin Rees. And just for the younger, I will show you a few slides taken from this grid debate to well understand what was the difficulty as long as only gamma ray observations were available. The main instrument observing gamma ray burst at that time was the Bose experiment. And BATSI again was made of several detectors which were just able to count photons and measure their energy, but not localize them. And it's only by comparing the flux in different detectors which have different orientation that a rough idea of the localization could be obtained. In fact, GBM is still doing the same today. It's based on the fact that you have a cos theta in the effective area of the detector for the gamma ray burst emission. And typically, BATSI was providing error box of a few degrees. There was a technique at that time which was much more efficient to give a localization. It was called the interplanetary network. It's still working. The idea is to collect gamma ray burst data from all available satellites in the solar around the Earth, and or even spacecraft in the solar system with gamma ray detector. And then by comparing the arrival time of photons, you can, by triangulation, provide an accurate localization. Here, the localization can be accurate because sometimes you can have a baseline, which is, for instance, of the order of 1 astronomical unit. The difficulty is that you need time to collect data, to check that the clocks are in agreement for all the chronology to measure correctly the delay. And at that time, it was only after a few days or even sometimes after a few weeks that the localization of the IPN was available, typically within 1 arc minute. And people tried to explore the error box with optical telescopes, but they never found something. And we know today that it could have worked with a delay of a few hours, but it did not work at that time. And so here are an example of arguments used by Bohdan-Paczynski to try to convince the GRB community at that time that gamma ray bursts were cosmological. So it was based, for instance, on this sky map of gamma ray burst after, it must be after almost 3 years of operation for BATSI. So each point is a gamma ray burst. It is in galactic coordinates. And you have to imagine that around each point, you have an error box of a few degrees. Okay. And so Paczynski explains that this sky map looks really isotropic. And then Paczynski says, okay, we know other population of objects with an isotropic sky map. For instance, nearby stars are nearly isotropic. This is something that everyone can experiment every night. But it's very easy to identify nearby sources like that because the proper motion is very large. I skip many details, but at that time, if gamma ray burst had an origin coming from very nearby stars, we would have already known. So then Paczynski explains, okay, most models consider galactic population. But look, here is an example of a sky map of a true galactic population, planetary nebulae, which are the last stage of evolution of low mass stars like the Sun. And clearly, it's not isotropic at all. We see clearly the galactic plane, okay, the Milky Way. So it does not look like the gamma ray burst sky map. Then, at that time, a lot of colleagues, for instance, like Dunlop, had developed galactic models for gamma ray burst, where gamma ray bursts were coming from a population of neutron star, which was not located in the galactic plane, but in a halo surrounding the galaxy. So Paczynski says, okay, we know a good example of a population, a galactic population, which is not in the plane, but in a halo. These are globular clusters. And then he shows the sky map of globular clusters. And clearly, it's not isotropic just because the sun is not at the center of the galaxy. And so we see an accumulation of globular clusters in the direction of the galactic center because we intercept a larger fraction of the halo. And you know probably that this is how Shapley in the 20s gave a first estimate of the distance between the Sun and the galactic center. And indeed, at that time, people like Dunlop had developed galactic models for gamma ray bursts, where gamma ray bursts were located not in a halo like for globular cluster, but within something which was sometimes called a super halo, which was much larger. And I think that at the very end of the galactic models, before the discovery of afterglows, this super halo was including, for instance, the large imaginary cloud. It was very, very large. And then Pashinsky shows the sky map of nearby galaxies. And again, it's not isotropic because we know that galaxies follow the large structures of the universe with filaments, clusters, etc. So we see, for instance, the Virgo cluster on this map. And it's only when you arrive to very distant galaxies, here Pashinsky is using a sample of radio galaxies, which are very bright, so which can be detected at large distance. It's only when you look at very distant objects that the sky map becomes isotropic, and everyone knows that this is one of the very important ingredient to build the modern cosmological model. This is including the cosmological principle. Here I should mention that there are no sources along the galactic plane due to the absorption. It's due to the method. It's not that there are no radio galaxies there. Okay. And so Pashinsky says this is this sky map which is the closest to the gamma ray burst sky map. So clearly gamma ray bursts are extragalactic. At the end of the great debate, I think that there was a vote among the assembly, which was composed mainly on people working on gamma ray burst, and still the majority voted in favor of galactic sources because of the energy, of course. Extragalactic models looked so extreme that they were very, very difficult to accept.
Frédéric, there's a question.
Yes, I see that. It's a good question. I never played this game, but then it would mean that you have a lot of, because the different galactic population I have shown are very different regarding, for instance, the stellar progenitors. So it would mean that you would have a very different progenitors for different gamma ray bursts, and probably you will distinguish these classes from the prompt emission, for instance. It would be very difficult to have exactly the same properties of the burst with so different progenitors. And in addition, for some of them, it's not very easy to reach the correct energetics and time scales. Most galactic models were using population of neutron stars at that time. And I see that there is a second, so yes, it's a good question. The question is, when you look at the histogram of duration, which is very important because this is how we distinguish the two classes, we see that there is an overlap around 1 second. And that's why this classification is difficult. Usually people make a classification which is, for instance, for the standard energy range. If you are above 2 seconds, you are a long gamma ray burst, otherwise you are a short gamma ray burst. But clearly with such a classification, you have some mixing. Some bursts are wrongly labeled. You can add other criteria which are also purely observational. There were some attempts about that, but it's not very easy. And probably you can have a better classification scheme if you include some physical understanding, but then it becomes model dependent. That's why I would say that most observers are not ready yet to use such more sophisticated classification scheme. But for instance, I don't know if I will have time today, but tomorrow I will discuss information about the host galaxies of gamma ray burst. And here there is a clear distinction between long and short gamma ray bursts, which can help a lot for the classification. Okay, so just to finish with this historical discussion, I show the final sky map of gamma ray bursts obtained by Batsy. Here it's really clearly isotropic, but in between, in 1997, we had the confirmation, thanks to Bose, that gamma ray bursts occur at a cosmological distance. So I will come to this. The idea is that you see that the main difficulty is the localization, because within an error box of a few degrees, you have millions of galaxies. It's very difficult to identify the source of the gamma ray burst. So you need a more accurate localization, and more accurate localization can be obtained only at larger wavelengths. The idea is that the solution was obtained with Bose, because for the first time on the same satellite, you had two instruments, a gamma ray burst monitor working typically in the standard soft gamma ray range used for gamma ray burst, and wide field cameras with a low energy threshold at 2 kV. So now we are in X-rays, which were aligned, so looking in the same direction. And of course, the wide field cameras had better localization capabilities, typically within 1 arc minute. So it's a big progress. And so it worked for the first time with GRB 970228. So you see that the nomenclature for gamma ray burst is very simple. 2 first digits are for the year, then the month, then the day. And the gravitational wave community has now used the same scheme for gravitational wave events. And so you see this burst. On the top, this is a light curve in the wide field camera. The wide field camera was the instrument providing the localization, and on the bottom in the gamma ray burst monitor, so at higher energy. So it's a nice long gamma ray burst. Then what happened is that it was found that with the X-ray instruments on board Bose, it was discovered that the emission was lasting longer in X-rays than in gamma rays. So the X-ray emission following the prompt emission is called the X-ray afterglow. And here I show the image of the X-ray afterglow obtained by Bose on the same day. So you see it's very nicely localized within 1 arc minute. And then you have the same field of view several days later. This is on March 3. And you see that the source has faded and almost disappeared. And this is an important property of afterglows, the afterglow emission, which is now observed not only in X-rays, but at all other wavelengths, is an emission which is very bright initially, and then is decaying very fast and disappears. Compared to modern satellites, Bose had no possibilities to compute the localization on board. So you had to wait for data to be sent to the Earth, so typically within a few hours, and then you had to compute the localization and send it to the community. So if I remember well, for this burst, the localization was sent typically almost half a day after the burst. I remember very well this day because I was a young PhD student working on the cosmological model of gamma ray burst, and so it was terrific to observe this observation. It was changing everything. So it was really a very important day in my life, even if I was for nothing for the discovery, of course. So the localization was sent to a network of interested people, and the team of Van Paradise organized the follow-up with optical instruments. And here you have the detection of the same source now in the optical. So it's called the optical afterglow. The first image is on the same day, and the second image is later. It's March 8, I think. And you see that the source is still there and has faded. And of course, by comparison with archive images, we know that the source which is labeled is here with OT for optical transient is a new source. It was not present in the sky before. So clearly it's an association. And now with this optical observation, we have a localization which is better than 1 arcsecond. So it changes everything. It allows, for instance, to have a deep exposure in exactly at the right position, or to do spectroscopy with a large instrument. For the event, yes, I see a question. Yes, usually the afterglow is always better localized than the prompt emission. There are some progress for the localization of the prompt emission with a technique which is so-called coded mask telescopes in gamma rays. This is used by BAT on board Swift, or it will be used, for instance, with Eclair on board SWAM. It can provide a localization within a few arc minutes, but it allows, for instance, for Swift to slew the satellites to have XRT entering the pointing towards the source. But then when XRT is finding the afterglow, the localization is much better. I don't remember, but typically 5 arcseconds, I would say, with XRT. So the afterglow is always better localized just because on average localization is easier at larger wavelengths. Okay. And so for the first burst 970228, the surprise was too large, and so there was no accurate spectroscopy immediately. It was obtained only for the second burst. But for instance, there was a long-term follow-up with HST, and here you have an image of the same field of view with HST, and you see clearly that the source is located in a distant galaxy. This is the host galaxy of the camera burst.
There's a question. There's a question
yes.
about the jets.
No, now we know, so it's an excellent question. Can we see the jets accompanying with afterglow? You see here, we are considered cosmological sources, so we cannot resolve at all the source and the jets. But on the third lecture, I will discuss the event associated with gravitational wave 170817, which is much closer because the distance is 40 megaparsec. And in this case, VLBI observation allow to see, for instance, a proper motion, yes, a proper motion of the source, and to see directly that we have a relativistic jet. But it's rare to be able to do such observation. It's too far, so it's not resolved in most cases. So here we have the first host galaxy, and then, as I said, for the second burst well localized with Bepo-Sachs, which was 1907-05-08, then teams were more prepared, and there was a spectrum obtained at Keck of the afterglow. This is the spectrum you can see on the left, and there are absorption lines in the spectrum, including the doublet of magnesium-2, and it is redshifted with a redshift of 0.8. And here now it's very clear, no doubt anymore, it's extragalactic. 0.8, there are no other solution. And later, once the afterglow has faded, you can observe the host galaxy at the same position, and you can again take a spectrum of this galaxy, and this is what is obtained on the right, and you see clearly emission lines in this galaxy, which again are redshifted exactly at the same redshift. So a very nice confirmation. So now we can do much better, but I show the light curve of the first afterglow, It's a magnitude versus log time, so you can see it as a log-log diagram for the flux, and you see that it approximately decays as a power law, meaning that it's a very fast decay. The very last point is obtained with HST on this plot. So it means that the afterglow decays very rapidly. That's why it's very difficult to observe. You have to react extremely fast. And it was a problem with IPN before Beposax. The accurate localization was obtained too late to discover something. So now we know that gamma ray bursts are at cosmological distance. Then from the observed flux or fluence, we can deduce the intrinsic luminosity or energy, which is radiated in gamma rays. And it's huge. It's clearly the brightest electromagnetic events known in the universe. For instance, the average energy radiated in gamma rays is comparable with the full kinetic energy of a standard supernova. And in a standard supernova, the light is only 1% of that. So it's really impressive. And then, of course, it helped a lot to better understand the physics behind. Nemirov played a funny game in 1993. He listed all models of gamma ray bursts. So I think there are 118 models in the list here. And I don't know if you can read it easily, but there is one column which is about the localization. So you have either cos for cosmological, or disk for the galactic disk, or halo for galactic halo, etc. And you see that most models are not cosmological. And once you know that they occur at cosmological distance, you can just eliminate most of these models. And the remaining models are variations around the same idea that I will develop now. I would like to say that I find interesting to try to imagine, I mean, these models were developed with serious people, with clever ideas. It would be very interesting to know if they describe astrophysical events that really exist and that still need to be observed. I don't know. It's a very interesting question. Okay, so for the afterglow, I show now a light curve in X-rays with a more modern instrument, which is X30 on board Swift. So here, the first part of the light curve is a bat light curve in soft gamma rays, which has been extrapolated to the X30 range. And then you have the X30. And you see that in the X30 light curve, there are several intervals indicated with dashed line. The first one is very interesting because it is a region which was not observed before Swift because of the delay for the localization with Beposax. And you see that if you have only the late evolution, it looks always the same, a power law decay with more or less the same slope. And it was a big discovery with Swift to see that the early evolution was completely different with a change of temporal slopes, still variability with flares. It's a very complicated initial evolution, which is asking a lot of questions to models, and I would say that it's not completely solved. Even if usually you consider that the physics of the afterglow is better understood than the physics of the prompt emission, I would say that there are still a lot of open questions related to this early evolution. I would like also to mention that the spectrum of the gamma ray burst afterglow is non-thermal. We will see that it's probably a synchrotron spectrum with a characteristic photon energy which decays also with time. Recently, you have probably heard of a very interesting observation with MAGIC of a burst above 100 GeV. It's very interesting because it extends the observation of the spectrum of this burst at very high energy. And it's a first case where there is a clear indication that there are at least two components in the spectrum. So it should, such observation should help a lot to better understand the physical condition in the emission region during the afterglow phase and to understand the properties, I mean the relative processes which are worked. For instance, here it's very indicative of a synchrotron plus self-Compton spectrum. Here I show the distribution of Swift gamma ray burst redshift, just to see that it's not only at cosmological distance, but on average, gamma ray bursts are very distant. The peak of the distribution is above the peak of the star formation in the universe. I will discuss that tomorrow because it says something about progenitors. And the record is above 8. So they're really at very large distance. And I won't discuss in my lectures the application for cosmology, but if you have questions, I can comment. So now I will summarize and go to models. So here it's a single plot to summarize the light curve from the prompt to the afterglow emission. So you see
Frédéric?
the first, sorry, yes?
Sorry, one question which I think is better maybe now. It's about the TeV photons. Why are they not observed in prompt emission?
It's a good question. The TeV photons are observed using, the Cherenkov telescope technique. So it's not directly the TeV photon which is observed, but the electromagnetic cascade in the atmosphere following the interaction of these photons with an atom in the upper atmosphere. And so these instruments have a narrow field of view. So there is a very low probability to have by chance a gamma ray burst occurring in the field of view of a Cherenkov telescope like S or MAGIC. So you need to point the telescope following a gamma ray burst alert. And for the moment, it remains difficult. In the case of the MAGIC burst I have shown, it's still nice, because I think that they start to observe 1 minute after the burst. So there is a possible debate to know if at the very beginning there is maybe a contribution of the prompt emission. Probably most of their observation is afterglow, but there is still some possibility of having a small contribution of the prompt emission. It is expected that with the next generation of telescope, you have probably heard of the CTA project, the Cherenkov Telescope Array. In principle, the CTA will be able to follow an alert within 30 seconds. And so there is a good hope to build a sample of gamma ray burst with the prompt emission detected at TeV energy. There is an additional difficulty because I have just said that gamma ray bursts occur at very large redshift. And you probably know that at TeV energy, you are limited by the interaction with the extragalactic background light. A gamma photon interacts with an infrared photon to produce a pair, E plus, E minus. So it gives an horizon for TeV energy. So it's only for nearby bursts that there is a hope. But CTA is sensitive already at 100 GeV, where this horizon is much larger. So there is a good hope. Okay, so I come back to this slide. You see here, you see clearly the prompt emission here. I don't know if you see my arrow. No, it's not working. I don't know why. So you see the first episode of emission, and then I will discuss tomorrow this initial steep decay, which says a lot and probably is a good indicator of the transition between two mechanisms, between the prompt and the afterglow. And then usually most light curves can be decomposed in a plateau phase or a shallow decay phase, followed by a faster decay. And on top of that, in half of the cases, or maybe a third of cases, you have variability occurring as flares. Okay. And for the prompt spectrum, thanks to Fermi, we know now that there are several components. The main one, which is observed by all satellites, and the additional component, which is revealed by the LAT. And thanks to the good coverage, spectral coverage of Fermi using GBM plus LAT, there is also a hint for maybe a subdominant additional component, even in the soft gamma ray range, a possible quasi-thermal component. I will also discuss that tomorrow because it could say something about the jet. Okay. So if there are no other questions about this observation, I will now start to build a model starting from this observation. So as I said, from the redshift, we know the distance, and then we can deduce the energy which is released in a gamma ray burst. The idea is that most models predict that this emission is produced by a jet and a relativistic jet, so the emission is beamed. But it's very difficult to estimate the value of this beaming. So the quantity which is easy to compute is a so-called isotropic equivalent gamma ray energy, which is the energy deduced assuming that the source is radiating in the same way in all directions. That's why it's called isotropic equivalent. And we know that the true energy is only a fraction of that. Typically, this fraction is the ratio of the true opening angle of the emission over 4 pi. Okay. So the result is huge, typically from 10 to 50 to 10 to 54 Ergs. And you remember that the rest mass energy of the sun is 2 times 10 to 54 Ergs. So we are clearly in a class of highly energetic events. These are the brightest electromagnetic events known in the universe. I mentioned in the diagram a recent study which is interesting, which is trying to estimate by using several catalogs what is the maximum energy of a gamma ray burst. Is it possible to measure a cutoff at high isotropic equivalent energies? And probably there is a hint for such a cutoff somewhere around 3 times 10 to 54 Ergs, which again says something about the physics of the central engine. This is a maximum energy reservoir. So we know that this energy is huge, and then we know that this energy is radiated on a short time scale. So it leads immediately to the idea that these events must be associated to a gravitational collapse of a stellar source forming a compact object, typically a neutron star or a black hole. And here I can stop briefly the keynote to just make this very simple derivation, which is important because it's common in the high energy astronomy field. So leave me 1 second to switch on my camera. So I have a homemade blackboard. And so the idea is the following. It's a very standard argument. So I hope, tell me if it's difficult to read. If you have some source, typically of stellar mass, with an initial radius, which is r dot, and if somehow it collapses, there is a gravitational collapse leading to a new compact source with a radius r. So you can imagine, for instance, a core collapse in a massive star, but you can see the merger of 2 neutron stars also as such a gravitational collapse with the central region collapsing into something more compact. Then we can try to estimate what is the energy released with such an event. So this energy should be estimated by comparing the total energy of the initial and final configuration. It's a little difficult without building the full structure of the object, but from the virial theorem, we know that the total energy is of the order of the gravitational energy. So we can just estimate this energy which is released by comparing the gravitational energy of the initial and final state. And as the final state is much more compact than the initial state, and as the gravitational energy scales as 1 over the radius, typically this difference of gravitational energy is dominated by minus the gravitational energy of the final state. So it is of the order of a number of the order of unity, the Newton constant, mass square, and final over final radius. And you can, of course, write that as the product of a dimensionless number, which is often called the relativity parameter or the compactness parameter, which is a ratio of the Schwarzschild radius or the gravitational radius of a source over its physical radius. So if it's low, it's a non-relativistic object. If it's close to 1, it's a black hole. And times the rest mass energy of the object. So for a black hole or a neutron star, this is above 0.1. And for a stellar mass object, this is of the order of 10 to 54 Earths per solar mass. So this is a way to release the necessary energy. And in addition, most of this collapse occur on a dynamical scale, which is very short, typically less than 1 second, and allows to release this energy in a very short duration. So I think that this ingredient is almost unavoidable. I do not know reasonable models of gamma ray bursts discussed today without an event, an initial event, which is somehow related to such a gravitational collapse. And then there is a second argument in favor of a compact source, which is the usual causality argument. If you have an emission region which has a size r, to be able to produce a signal varying on a time scale which is t var, which can be very small in the case of gamma ray burst. It's difficult to quantify, but it's at least of the order of 10 milliseconds in many gamma ray bursts. Then, from the finite value of the speed of light, the causality says that the source must be smaller than c times this time scale. Otherwise, you would have a delay effect that would smooth out the emission on longer time scales. So it goes in the same direction, because for 10 milliseconds, it corresponds to 3,000 of kilometers. So, okay, you could say it could be a white dwarf, but there are not good models with white dwarf, but the only remaining objects are neutron stars and black holes. And there are good evidence that in some gamma ray bursts, the variability is maybe occurring on the 1 millisecond time scale. And then in this case, there is no doubt that the central source has to be either a stellar mass black hole or a neutron star. So I don't know if there are questions about these two calculations. Otherwise, I will come back to the keynote. It's okay? Okay. Okay, so we have these two indications that we have a gravitational collapse and we form a compact source. So then the next argument is a little more technical. The idea is that once we know what we have just learned, the fact that the prompt emission is a non-thermal gamma ray spectrum extending well above 1 MeV says that this prompt emission cannot be produced close to the central source. It has to be produced by a relativistic ejecta escaping from the source, and it has to be produced at large distance from the source. The idea is the following. If you take the huge energy we have deduced from observation, and if you put it in a small volume around a black hole or a neutron star, so let's say, I don't know, 100 kilometers or something like that, the density of gamma ray photons is so high that there is a very high probability that these photons will interact to produce pairs. So you know the gamma-gamma reaction producing a positron plus an electron. This is the main idea. So we want to avoid a gamma-gamma reaction. Otherwise, we will suppress high-energy photons and won't observe it. I see that there is a questions. Yes, it's a good question. Here, when I started to discuss the energetics, I have included only gamma ray photons. We expect neutrinos to be also emitted, somehow it should be taken into account. But to my knowledge, at the moment, it's very difficult to estimate what is the corresponding energy. There is no clear association of a single gamma ray burst event with a neutrino emission. So it will be for later. Here I have in practice, for the moment, I have identified an energy reservoir with this gravitational collapse, which is large enough to cover everything. Gamma rays, neutrinos, gravitational waves. The main difficulty is to identify the mechanism to extract this energy, to convert this energy. Do not convert directly gravitational energy into gamma rays. There are several steps. So I come back to the gamma argument. So for a pair production, there is a threshold, of course, because you produce leptons with a mass which is 500 keV. And then the threshold is written on the slide. So typically, high energy photons interact with low energy photons, and you need the product of the two energies to be above a certain value, which depends on the interaction angle theta between the two photons. And the cross-section of the interaction is also well known. I have plotted it as a function of the energy of the low energy photons for several energy of the high energy photons. And you see that it is peaked at an energy which is more or less twice the energy of the threshold. So you can get a good approximation of the full cross-section by just considering a Dirac function at an energy which is twice the threshold. And this is what I have written here. And so the idea is that if you compute the mean free path of gamma ray photons in a very compact source for this gamma ray energies, the density is so high that the mean free path is much smaller than the size of the source. So most gamma ray photons should interact and produce pairs. And there is no hope to obtain a non-thermal spectrum with what is observed. You should observe a thermal spectrum produced by the produced pairs and with a clear cutoff above 511 keV. So this problem is well known and has been solved since the 70s for other extragalactic sources. The idea is that the solution is the relativistic motion. If now the emission region is not a static source, but is a jet, for instance, moving at relativistic speed, there are two effects. Both are related to the beaming, the relativistic beaming of the emission in the direction of the motion. You know that typically, if emission is isotropic in the co-moving frame of the emitter, then in the lab frame, emission is beamed within an opening angle, which is of the order of 1 over the Lorentz factor, 1 over gamma. And so the idea is that if gamma is large enough, you do not see the whole emitting region because most parts of this region emit photons in a direction which is not yours. You see only a very small region which is coming towards you. And the causality argument should apply only to this small region. We will see that it allows to multiply by gamma square the size, the deduced side of the region. So the region can be much larger than what you thought previously. And if the region is much larger, it means that the photon density is much lower. So it will increase the mean free path. And the second argument is the fact that the cross-section depends strongly on the interaction angle. And in a static source, if photons have an isotropic distribution, you have a large probability of face-on collision, which has the largest cross-section. But now, if photons are emitted by a relativistic ejecta, as they are beamed due to the relativistic beaming, all photon paths are almost parallel, and the most probable angle of interaction is between 0 and 1 over gamma, and it leads to a strong reduction of the cross-section. And so you see that when gamma increases, when the Lorentz factor increases, both effects go into the same direction, and then you can compute the minimum Lorentz factor to have a mean free path, which becomes larger than the source, than the size of the source, so that the source becomes transparent for this process, and you can observe an ensemble spectrum. And typically, you get a Lorentz factor of 100. So I had planned to make this calculation, but I see that it's already 1:25, so I don't know if it's a good idea to do it now. I will maybe leave that for tomorrow. Okay, I will leave that for tomorrow. So I will come to something that it's easier to discuss now. I will tomorrow give more details to obtain this important constraint on the Lorentz factor of the ejecta. But here I can show the few cases where there is a direct evidence for such a relativistic motion in a gamma ray burst. So it is usually based on radio observation, because this is where you have the best space resolution. So the first method is based on radio scintillation. You observed a source which is initially very small. So you observe a strong scintillation because the angular size of the source is smaller than typical inhomogeneities in the intervening medium. And then at some point, due to the relativistic expansion, the angular size becomes larger than for inhomogeneities, and scintillation stops. And from the instant of the transition, with some knowledge about inhomogeneities in the intervening medium, you can deduce the apparent size, the angular size of the source at the moment of the transition. And then from the duration since the gamma ray burst, you can deduce the apparent speed and observe a superluminal apparent motion, which is a clear indication of an intrinsic relativistic motion. Another possibility is using VLBI to directly measure the angular size of the source. It has been done in a very limited number of cases of nearby events. I think that the best case is GRB 030329, which is plotted here. And again, from the measurement of the angular size, you can deduce a proper motion, which is superluminal. And when we say superluminal, you see that it is really superluminal. Here, the initial apparent velocity is 5c. Okay, so it's a clear indication that intrinsically we observe a relativistic motion. And I will show during the third lecture a very spectacular application of this technique for 170817 with a VLBI observation. And now the source is only at 40 megaparsec, so it was a good case to use that. So there are direct evidence for the relativistic motion, but in most cases we do not have such direct evidence. That's why we have to use the indirect constraints of gamma gamma to deduce the Lorentz factor. That's why I think it's useful to do the full calculation, but I will do it tomorrow. So I don't know if I should stop here or if I still have 3 minutes to summarize what I did.
Summary would be
there
good.
is a question about scintillation effect. I don't know, maybe there are radio astronomers in the audience who would know better, but because I must say that I must confess that I do not know a lot about scintillation in the radio range. So probably there is a dependence on frequency, but I don't know, I must say. So I don't know if someone wants to answer. I'm ignorant about that, I'm sorry. So maybe I can show a last slide and I will start again with this slide tomorrow. So if I summarize, we know that we need an initial event, which is typically a gravitational collapse on a short-time scale, leading to the formation of a stellar mass compact object. Typically, it's either an accreting black hole, or there is also some discussion about possibly a highly magnetized neutron star, a so-called magnetar. And what is interesting is that we know typically two channels in the universe for such events, either a core collapse of a massive star or a merger of a compact binary system. And we have two classes of gamma ray bursts. So it's tempting to associate each class to one channel, long gamma ray bursts with core collapse and short gamma ray bursts with merger. And tomorrow I will show you that there are now excellent observational evidence for this association. And then with the argument I just gave about gamma gamma, we know that we need to produce a relativistic ejecta. So tomorrow I will explain the calculation to deduce gamma. I will also give a few ideas about the relativistic ejection, but I don't plan to give too many details. It's a very complicated physics, and I'm not the best expert on that. I will try to focus more on the second part on these diagrams that I won't comment today, which are the internal dissipation in the jet responsible for the prompt emission, and the interaction of the jet with the environment, which is responsible for the afterglow. I will first try to compute with you the characteristic radius for all this process, and then try to discuss possible mechanism and relative processes. Okay, so should we stop here? Of course, if there are still questions, I can take them.
I guess if questions are there, it would be good to have them now. Pratim, okay, I'm unmuting you.
Yeah, sorry. I actually, the thing is, I wanted to apologize for the comment. Actually, the question that I wanted to ask, but it got horribly wrong, and then I lost my connection. So I couldn't hear most of the talk because of my connection. But I saw a slide in the initial slide where you have made a comparison between an observation which was done with both gamma ray and optical in the optical regime. So I just wanted to ask you, and I don't know much about either optical astronomy or gamma ray astronomy, but I see like, yes, so I see that in the, yeah, so you have what I see is at the end, there is a scattering kind of a tail, or I don't know whether, is it actually called a scattering tail at the end? And if it is so, then like I know from radio astronomy, from scattering tail, you can get observation. So you can say something about the propagation or the paths of propagation. Can you say something like that for this? And I also see like if in the previous slide, the next slide, when there was this plots for different energies. For the lower energies, you again have something like a scattering tail, which is, yeah, which, right, exactly. For the, I think for the lower energies, you have some form of a scattering tail, which is kind of, like if it goes as lambda to the power 4, this is what we expect, that for lower energies, we have a longer scattering tail. But like, I just wanted to understand that.
What do you call exactly scattering? Is this short-time scale variability we see in the light curve, or?
So it's basically, so I know in radio astronomy, you have a lambda to the power of 4 kind of a tail that you get. So I thought like, if there's some analogy to that, like I actually don't know. So that's why I wanted to ask, like on the right-hand side, the right end.
So I'm sorry, I'm not sure to fully understand, but what I can say is that if you look on the black light curve here, which is a gamma ray light curve, so you see that there are variations on very short time scales. And of course, what is very difficult here is to distinguish if this variation is physical or for the shortest time scale, or if there is if it's just due to the statistic of the detector plus the evolution of the background, whatever. It's very difficult, and that's why it's very difficult to measure very precisely the shortest time scale of variability, which would be a very important constraint for the central source, as I have explained. That's why I used a very conservative value in my estimate, where I took 10 milliseconds. But we see the light curve varying on 1 millisecond. The difficulty is to know if it is physical or not. I'm not an expert on that. It's very difficult on the point of view of the analysis of gamma ray data to measure that really properly. And then what is very interesting to notice on this light curve, it's something that can also be seen when you compare gamma ray light curve, is the fact that the light curve is not the same at all energies. We see some shift. For instance, clearly the optical light curve starts later and lasts longer than the gamma ray light curve here. And here you see that, for instance, at low energy, the first panel on the top, the light curve remains very active for a very long time, whereas it's not so clear that it's still the case at higher energies. This is very interesting on the point of view on the modeling of the prompt emissions, something I will discuss tomorrow, because it says something about the underlying spectral evolution. If the spectrum is evolving during the emission, for instance, become softer, it can very easily explain the fact that you do not observe exactly the same shape of the light curve at various wavelengths.
Sorry, again, I couldn't hear the last part. So you're saying that for the lower energy, so this is what I was saying. At the lower energy, you have like a tail which is going on for a really long time, which you don't see as you go for higher energies. Exactly. From that, can you say something about how the gamma rays are propagating, or in the path of the propagation of the gamma rays? Or you said something that you can see, you can model, which I couldn't hear.
So from the observational point of view, I can deduce that the spectrum of the gamma ray burst is evolving. And then from the point of view of models, I can deduce about my model, but that the conclusion depends on my model. But for instance, in one possibility, which is the production of gamma rays from internal shocks propagating within the ejecta and accelerating electrons, it can say something about the location of these shocks and their propagation. So okay. It's a very important feature. I will show some examples tomorrow.
By location of the shocks, you mean the atmosphere around the shocks?
I would like to know, for instance, at which radius from the central source shocks are forming. Do they all form at the same distance? How do they propagate in the ejecta? Such questions.
So, Apratim, I'll move to the other question.
Yeah, sure, thanks.
I see that there is a question about the mean free path slide. I will comment that tomorrow because I will do the calculation.
Okay, so I've unmuted Surendra Padamata.
Yeah, so if I understand correctly, when I asked the extragalactic nature of this gamma ray burst, you said there are two proofs, and I understood the first proof in terms of sources being isotropic, and you can only explain them being isotropic by assuming an extragalactic distribution of these neutron stars because of required energetics and everything. And when you came to the second proof and you tried to explain it through the radio afterglow, and I didn't clearly understand, but were you actually trying to say that there is a redshift in the spectrum of the afterglow, and this is somehow correlated to the redshift of the galaxy? And since we know the host galaxy, and that is how we know the distance to the GRB, And if that is the case, how do we actually know that there is this redshift in the spectrum of afterglow? Is it something, a standard shape for this afterglow? So that's where I got a confusion.
Okay, so first I should mention, because maybe I was not clear about that, that we have now afterglow detection and redshift measurement, both for long and short gamma ray burst. So both populations are extragalactic. For short gamma ray burst, the difficulty is that it's more difficult to localize them. So the fraction of short gamma ray burst with a well-measured afterglow and a redshift is lower than for long gamma ray burst. So it's one difficulty. And another difficulty is that if you look at the sample of short gamma ray burst with a BATC, for instance, there is probably a contamination of this sample with other classes of events. It's a complicated population. It's not completely clear if it's a very homogeneous population or not. But I will discuss only the two main populations. So the idea is exactly that. We have now many cases where the same succession of observation was done, localization of the afterglow, absorption lines in the spectrum of the afterglow which are redshifted. Then the afterglow decays, it disappears, and at exactly the same position we find a distant galaxy at the same redshift. There is no doubt now that this redshift is the redshift of the source producing the gamma ray burst. And as these redshifts are very high, I mean the record is above 8, there is no other possibility than a cosmological origin for this redshift, the expansion of the universe. You cannot produce such a redshift with a Doppler effect or with Einstein redshift from a gravitational field. So I think there is no doubt about the cosmological origin of the, at least if you want to be very conservative, at least of the majority of gamma ray burst. And the main difficulty now is to have to try to improve the fraction of burst with the redshift measurement. This is something we are working on within the SWOM mission to try to improve the follow-up with dedicated instruments and a well-thought pointing law to try to increase the fraction of gamma ray burst with a non-redshift, which is about 1/3 for SWIFT, which is the best instrument currently working for localizing the afterglow and allowing the measure of the redshift. So I don't know if it answers.
Okay, but then okay, that answered partially, but what if we don't have a contamination? I mean, do you actually have contamination in every GRB that you measure, or that's the?
You have to understand that.
I mean, what if you don't have these absorption lines?
You have to understand that when you look at the BATC catalog, for almost all gamma ray bursts in this catalog, we have only the prompt emission. And for the shorter gamma ray burst, often the signal is detected only in a few bins. So it's it's not a very precise information, and it's very difficult to discuss possible contamination, for instance, by it's very possible that there are a few giant flares of soft gamma ray repeaters, for instance, things like that. It's and then I see that there is a question about more exotic progenitors. So there are indeed.
Just one moment. I think there's a related question from Dimple,
okay.
Slightly above, about the spectroscopy and.
Okay, please.
So what is written is, regarding the location of GRBs, without spectroscopy details, how can we estimate the redshift of GRBs, as the spatial coincidence with the galaxy may be a chance coincidence?
Okay, so so yes, if there is no spectroscopic redshift of the afterglow, But if the localization is still accurate so that the host galaxy can be identified, then it's just statistics. Knowing the population of galaxy, you can estimate the chance of just a spatial coincidence. Usually, due to the distance, this chance coincidence is not so high. But there are also cases where you do not have a good localization. So you don't have the host galaxy. For instance, most Fermi bursts, if they are not detected also by Swift, there is no afterglow, no host galaxy. In this case, I would say it's impossible to estimate the distance. There were some attempts to do that using some correlation between the energetics of the gamma ray burst and the spectrum, the so-called Amati relation or Yonetoku relation. I will say a word about that tomorrow. You can see that as a similar method as the standardization of 1A supernovae, allowing to use them as standard candles. But I would say that there is a big difference with gamma ray burst because, in fact, without the standardization, 1A supernovae have already luminosities at the peak which are very similar. Here there is a large range, so you need to do a very important correction. And it is based on a correlation which is highly debated and which is not physically understood, which is not the case for 1A supernovae. Even if it's not entirely understood, we know that it's an exploding white dwarf, and then we know that the Chandrasekhar mass should play a role in the fact that they appear as standard candles. So my opinion on that is that it's very dangerous to use these correlations to try to deduce a redshift. So I would not do it myself. So if there is no afterglow, there is no redshift.
Okay. Now we have that question on progenitors.
Yes, so indeed there are exotic progenitors which have been proposed. I'm not an expert in these models, so I don't really plan to discuss them. But for instance, I will show tomorrow that there are additional observational evidence that I have not shown yet for the association of long gamma ray bursts with core collapse, which would not fit, for instance, with evaporating primordial black holes. Which is a suggestion is the question. I know that this idea of Hawking radiation in the gamma ray range for primordial black holes has been proposed it cannot be excluded, let's say, for a subpopulation of short gamma ray bursts in the basic catalog. And as we have no information about the distance, about those galaxies, it's very difficult to go further than just say it's compatible with. This idea is very difficult to prove observationally, I would say.
Okay.
So I'm an astrophysicist. I will focus more on the more standard models where we have clear evidence observationally.
Okay, so I guess there is one last question. No, okay. Is there any more question? Otherwise, maybe we could. Thanks. We could thank Frédéric for this wonderful lecture, and thank you everyone for participating actively.